If you want to do well in thermodynamics, it is critical to compare ideal versus real gases. And this is not a long or hard topic, but it is very important. Now, this is our beloved ideal gas that we probably know from high school, modeled by the equation PV equals nRT. And we got a bunch of molecules bouncing around in here. And the important thing about these molecules is that there are no intermolecular forces, no attractive or repulsive forces between the molecules. Also, when they collide elastically, so there's no loss in kinetic energy with every collision. There's negligible volume, so compared to the size of the container. So if you look at this container, an ideal gas would take up almost no space. Now, this is a very poor example because the molecules take up a lot of space, but in an ideal gas, there's like no volume. And then also they obey Newton's laws of motion. Now, let's compare that to a real gas where there are intermolecular forces, and those forces can be either attractive or repulsive. Now, if attractive forces dominate, then there's stickiness between the molecules. They attract each other and they kind of pull themselves in a little bit. So if we compare an ideal versus a real gas, the pressure of the real gas is going to be less at the same temperature and volume because there are less collisions against the edge of the container. Do you see that? Now, if we want the pressure to be the same between the real and the ideal gas, then we either need to increase the temperature, so we need to make those molecules move faster so they bang against the edge of the container a little bit faster, or we need to decrease the volume, make them a little bit more crowded so that they're pushing against the container. Now, this is extremely important. When molecules come together, particles of gas, and attractive forces dominate, then potential energy decreases. The analogy is an apple falling from a tree. The gravitational potential energy decreases. Kind of similar here, where they're attractive forces, they're pulling them in, that decreases the potential energy. Think of like pulling it away. It takes energy to pull it away. Now, when they come closer together, the attraction is stronger, but it's stronger in a negative sense, which means overall it's lower. Okay, now if repulsive forces dominate, the particles are really crowded together. They're like pushing into each other and they repel each other just literally because of the size of themselves. The electron clouds repel, the nuclei repel, and you can think of it as like two magnets. You're trying to push two magnets of the same pole together, they repel each other. Now, if you try and push those magnets together, it takes energy to push them together. So when repulsive forces dominate in real gases, as the molecules come closer together, as they become more crowded, potential energy increases. And that also is super key. When repulsive forces dominate, a real gas will have a higher pressure than an ideal gas at the same temperature and volume. And that's because those particles are kind of pushing away from each other and they're colliding with the container more often than with an ideal gas. If we want the pressure of a real gas and an ideal gas to be the same, then we either need to decrease the temperature to slow that real gas down so it's not banging against the container as often, or we need to increase the volume to give them a little bit more space to breathe. So that's it. Super critical summary, short and sweet. Our beloved ideal gas modeled by our equation of state PV equals nRT. Most important thing is that there are no intermolecular forces and no potential energy is stored between the particles. But for a real gas, there's a different equation of state. It might be close to PV equals nRT, but it'll be a different equation. And also very important, attractive and repulsive forces will affect the values of pressure, volume, temperature, and other state properties. And there's potential energy that's stored within the intermolecular forces of a real gas. I'm excited you're on this thermodynamic journey with me. We're building a strong foundation for you to do well and maybe even enjoy thermodynamics.